making this video for all of you who are in quarantine and away and aren't going to be there the day we actually go through the plate tectonic simulation. This is the last big activity for Unit 5 on plate tectonics. We started in continental drift, went through seafloor spreading, and we're going to cap it off with plate tectonics here. So in this simulation, we're going to look at different kinds of crusts and how they interact in at different plate boundaries. So first off, if you have the packet, I'm going to skip through some of the questions and just hit the highlights for the pre-lab questions and part 1. First off, let's talk about you. You float in water because you are less dense than the water that you're floating in. All right? A rock will sink because it is more dense, and in that way, the different types of crust float in the mantle. The ocean crust here, if you look at the little legend down here, is a little bit less dense than the mantle. All right, it's mostly made out of basalt, as we discussed in VCAS 5, and how that basalt records important magnetic information. The continental crust is much less dense compared to both of them, but way less dense than the mantle, and it is made mostly out of granite. All right. So that's the main thing that we need to discuss to set up these next couple of simulations. So let's jump right into the first simulation. So where plates interact, different features are formed, and those features will tell us what's happening at these plate boundaries. This is why it's super important to see these diagrams and see how they're formed. So in a convergent plate boundary, so when they're moving together, and again, in VCAS 6, depending on when you watch this, you may have already learned a little bit about convergent plate boundaries. The ocean plate is subducting underneath the continental plate, and some of it begins to melt, begins to rise, and form these volcanic mountains. So in your notes, or in that lab, it asks you to diagram out several different things, such as the types of crust. So this is continental crust. This is ocean crust. We have the mantle. Most of this red stuff. And let's see here. We've got a trench. And all of these are volcanic mountains. And we had this thing moving in this direction. So if you got your packet, and we are in part 2 of that packet. There are 4 questions, A, B, and C, that go along with this. So let's go through them right now. So first off, this feature right here, where the crust is actually going underneath, is called subduction. We know that ocean crust is denser than continental crust, and this will help explain why the ocean crust will always subduct underneath continental crusts. Right? It's because it's more dense than the continental crust. But what you may have noticed, you may not have, it doesn't show up really well on the images that printed out, that there are these bubbles right in this area, okay, that formed up and welled in this one area to form these volcanic mountains. That's what B is asking about. This is actually magma. All right, magma formed when the ocean crust subducted into the mantle. All right, and because it's less dense than the surrounding, bubbled up to the surface, and that magma then formed these volcanic mountains. So we're going to go ahead and put that in here as well. Now, let's talk just a moment about that. Many students have a preconception that the mantle is a liquid the fact that it's made out of magma. This is incorrect. The mantle is chemically different than the ocean crust and the continental crust, and most of the mantle is actually still solid. It's just a more plasticky solid. All right, it can flow under pressure. So where does the magma come from to form volcanoes? A lot of the times it's when a plate is subducting underneath, melting, and rising up to the surface. All right, that will help with D. So quick summary again of what's happening in this. When two plates, an ocean crust and a continental crust, collide, the ocean crust subducts, melts, causing that magma that is less dense to rise up through cracks in the continent and form these volcanic mountains. So notice this is the profile that we drew a few days ago, if you were in class, where we had a trench and the Andes Mountains in South America. And I asked, how do these things form? What's going on here? This is an example of that Nazca plate, which is out here, an ocean plate, subducting underneath the South American continent, forming these volcanic mountains, the Andes Mountains. So let's take two types of ocean crusts and slam them together and see what is different. So like in the previous one, we still have ocean crust. That one of them does get subducted, begins to melt, and that magma that is formed from this melting bubbles up. And the reason for that, I believe, is that some of the material that is dragged down with this, some of that water and the sediment acts like a flux material. Flux is just something that helps a material melt at a lower temperature. So this stuff bubbles up and begins to form volcanoes. So let's diagram out this one. All right. Again, we have ocean crust. In this case, this was the older ocean crust in the simulation. And the young ocean crust. All right, we had the mantle, again, that these things are floating on, even though they're both still solids. The crusts are floating like you float. We got that magma rising up. We've got another trench here. And a bunch of volcanoes. So we can infer, based on the fact that the older crust here is the one that's subducted underneath, that it is most likely the denser of the two. That's why it subducts underneath. And let's take a look at some examples. So a good example of these volcanic islands forming actually is in the Pacific. Right? There's something called the Ring of Fire in the Pacific that is a line of volcanoes or a string of volcanoes that almost encircles the Pacific plate. This is the Pacific plate. And every place that you see this trench, on the other side is some kind of volcanic feature. In fact, if we zoomed in here to Guam and Saipan and things like that, this is the Philippine plate, this the Pacific plate. And we have this island arc of volcanoes. And the question is, which of these plates is doing the subducting? Well, the Pacific plate is the one that's subducting. And we know this because these volcanic islands have to form when a plate subducts under the plate that they're sitting on. Right, and that magma from the subducting Pacific plate wells up to form those volcanic islands. So these volcanic islands are always on the non-subducting plate. Okay, now let's see what happens when you have two continents colliding. All right, so not a ton we need a diagram on this. All of it's continental crust. Still got the mantle. And two continental crusts colliding. So there's two big questions that I ask for in this. And one is, what's different about these mountains compared to the other mountain-like features in the previous? And the answer is, the other two had volcanoes from magma rising up, and this doesn't. These are just normal mountains. And the reason that there are no volcanoes in this is because neither one of these plates subducted. Now, I always ask why, and students always say something about they have similar densities. Well, I could probably come back to this one and argue that the densities in these plates probably aren't that drastic. They're both ocean crusts, all right, both in basaltic composition. And likewise, the continental crusts here are probably very similar in composition as well, so probably not a big difference in their densities. But what is different here is their densities of the continental crust compared to the mantles, and the ocean crust compared to the mantle. Now, we float in water like an ocean crust. We are slightly less dense, so we barely float in the water, where continental crust is more like a big balloon or beach ball that floats way out of the water. And with that analogy, it's not that hard to push someone underwater. It takes just a small force. So that's why ocean crusts subduct so easily into the mantle, where continents are so much less dense than the mantle that they're floating in, that it's impossible to get one continent to push another one under. You can have continents actually slip one underneath one another, but one does not actually subduct under or into the mantle because of such a low density. All right, let's finish up with the last two simulations then. So if we, instead of doing a convergent plate bend, we do divergence, which is the next diagram in your packet. And we let them drive away. We take what was one continent and we split it into two. So let's diagram out this one. So continental crust, you got the mantle. All right, there's some magma rising here. And let's draw the arrows with a ridge. Now it's hard to see here. The world is actually remarkably flat. So it's hard, some students miss it, but if we did an exaggerated profile, so we stretch out it, you'd still get something like we made in the previous labs, right? It's there, it's just harder to see because we're not looking at the topography, we're looking at the motions. So a few things I want to mention. First, this is a good example of the MidAtlantic Ridge. This is why the continent shapes match up so well. The continents were together with Pangaea. The Pangaea began to split apart along the mid-ocean ridge and were carried away from the ridge. What's happening here again is that the ocean crust breaks apart here, magma rises up and makes new ocean crust. So if we were going to put some extra labels in here, I would argue that you may want to describe how the young rocks are found along the ridge and the older rocks, right, are actually found out here. And that'll go into, or I described that a little bit when we did BCAS 5. The final one that we want to get into deals with a transform boundary. All right, transform, if we're going to use, let's reset it. Transform, go. So when they're grinding past one another, and not a whole lot happens. So if I were to sketch out what had happened here, again, we still have arrows indicating the movement, but they're just sliding past one another. You have your continental crust and the mantle. You may get some crumpling in here, but there's really not any big mountains that get formed, no volcanoes as far as volcanic mountain ranges. This does allow weaknesses and cracks in the crust, so you may get some volcanoes on either side, but you're not getting these big mountain ranges like we have in the past. So that's the information that you need. So hopefully you can finish up the post-lab questions for the plate tectonic simulation. There should be a Google Doc that you guys can edit. If you can print it out, that'd be great. There are also, I think I put some spaces in there so that you can take these, either mark on the actual diagrams or take screenshots of these different diagrams and place them in there for your notes. Very, very important that you get a good set of notes on this stuff and with VCAS 6. So I hope that'll help.